go back to the lecture on evaluating trees. So we already have some introduction about the distance methods and also the maximum parsimony method. And once we got a tree, we really want to put some evaluation on the trees we got to see how well supported it is. And one way is to look at the property of the tree, which means the consistency index. And right now, I'm going to introduce some other index you commonly see on the branch of the tree. You read in a paper, and that's called a bootstrap support. And also some other people also use strychnine or Bremer support for the other purpose. And I will talk a little about them as well. So let's start with the bootstrap. And bootstrap support can be applied to all the distance metrics and also the maximum parsimony and also the maximum likelihood, although nobody actually uses this for ML, the maximum likelihood. It takes too much time. But it's very common to use it when using distance methods like neighbor joining. It's very common. For parsimony, it's also very common as well. So what does it do? And basically, it's a kind of a resampling process to see how well support the data for a particular tree or a particular topology of the tree. So since the best way actually is to, for example, if we want to have some measure for a certain hypothesis, the best way is to go back to the population and resample again, and you can get obtain a mean of the sampling, and you'll have a better support or the value for the actual mean of the population. But since it's almost impossible to do that, and in practice for the molecular evolution, you can do that again. For example, if you go back to all the material again and sample another sequence and get another estimate about the tree. So it's the same thing actually, similar idea. So the best way is to go back, but in reality, we don't want to spend the time and money and the effort again. So how about for the data we already got at hand? So that's something we can do using a pseudo resampling process. So this diagram is just showing the two differences between the actual resampling from the population and the pseudo resampling process from the things we already got. On the left, that's the true resampling process. This is the population mean, and we can go back to the population and resampling and to get a confidence interval for the mean. And for the pseudo replication process, then we can basically go back into our already obtained data matches and sample from those data matches and remake a data matches and estimate the mean from the new data set. And since this sample, the new sampling is from our data set, so this is kind of a pseudo resampling process. And how do we do that? In bootstrap method, it can basically go from this diagram from the top. The original data matrix has a dimension of n, the character and also the taxa. It's a large data set. So for a new resampled data matrix, we basically just choose one of the characters randomly and put into the first position of the character. And the order of the taxa is still the same. So for example, for character, the site 1, we basically select number 7 of the characters and as the first site. And the second site is from the 33 of the character, and then 29. So it's possible that you resample again for a particular character. Like in this case, on this side, the 7th character is resampled again. So the new data set has the same character number as before, but it's kind of rearranged in a way, and also it double count some of the characters, which means that some of the original character will be omitted or be eliminated from the new data set. And for the new data sets, you can make a new tree based on whatever method, the neighbor joining, maximum likelihood, or maximum parsimony, any kind of tree, and still go through the same process we already introduced for making MP or NJ tree. And this process is the same. So it takes the same time from here to here. And for the second data matrix, we kind of duplicate this process and to make a lot of replicates of this data matrix and make a single tree out of this new data matrix. You can replicate 100, 500, 1,000 times. It totally depends on the time you got, because one additional data set will take the double amount of the time you already got for any particular analysis, NJ or MP. So of course the number is the higher the better, since it's a statistics process. So just like flipping coins, it's better to have 1,000 is better than 100. It totally depends. But if you for neighbor joining, it's if one analysis takes 1 second to finish, then if you want to replicate 1,000 times, it will take 1,000 seconds. So if it takes 1 hour to finish the maximum parsimony, then again it will be 1,000 hours if you want to make 1,000 replicates. So it's a long process, but it's very very useful in doing so. So after you got, for example, 1,000 trees out of those new replicates, we make a consensus trees out of it. And you usually use the majority rule tree, which means the over 50% of the trees will be marked and consensus into a new tree. And I prefer to use another way is to actually take the number and put it back in onto the actual trees we got. Like for example, we got a neighbor joining tree, and then we collect those numbers and put the numbers and pass onto the original neighbor joining tree, because that is the tree actually from the original data set. And this is kind of a twist of the data set. We are kind of playing around about the sampling. So because this resampling process, we can imagine that there's some weighting and unweighting for the particular characters. And the purpose is to eliminate the noise, the potential noise from the data set. So, and also to put some more weights on the true informative character size. So basically this is kind of a test for the robustness or internal support for your data sets to a particular hypothesis or the given trees from neighbor joining or neighbor maximum parsimony and so on. So this is basically the process for the bootstrap method, and we will discuss about the weakness and about it later on, but we just continue on for the JER-MING method. And for the JER-MING method, the process is very, very similar. The only difference is they do not put on any extra weighting on the character. So they only eliminate certain part of the character, but they do not double count the size in this case. So for example, they only takes out like a 20% or 5% of the characters. You can specify that on the analysis. So the final outcome of the new data matrix will have only n minus x characters if you eliminate, well, actually that's not a percentage, or take out x of the characters. And again, make the new tree and make a consensus tree out of it. So the only difference is they don't overweight a particular character, but they want to eliminate the noise. So that's the idea. And the actual, in practice, the two methods will almost give you the identical result, basically. They don't differ that much. So this is the example, a real example we got, and from some of the primates phylogeny. And this is based on the maximum parsimony criteria and bootstrap 1,000 replicates. Then that's the outcome table you can get. And here, this is how you read from the output. So for the taxa, we just number the taxa at the end, like 1 to 7 for the taxa. And here you will see 1 to 7, that's the taxa order. And then that's the frequency we got from the bootstrap analysis. And for the star means that these two things are grouping together. Like, for example, the 6 and 7, they group together. Then it has a 1,000, this is based on 1,000 replicates, so the frequency would be 100%. So 6 and 7, that's right here. And you have to look from another direction. It's this branch. So this branch has 100% support of the bootstrap value. For 4, 5, 6, 7, that's 99.9. So the 4, 5, 6, 7, okay, it's this one, and it's just round up to 100. There's no digit there. And for that too, 5, 6, 7, there's 94 over there. But look at over here. So there are two numbers are actually lower than 50% from the bootstrap analysis. But the information is here. So 2 and 3 are actually supported by 49.7%. So although the actual consensus tree does not resolve 1, 2, and 3, it almost is kind of marginal support for 2 and 3 to group together. So actually, the consensus tree, you probably cannot see that, but from the table you can see these things as well. And also you will see there's another number from 3 to 7 is grouping with 48%. So this is probably the reason why it was not resolved, because number 3, the gorilla, sometimes is half of the possibility will group with 2, but the other half will group with the others. So that's why it kind of flipping around. That's why it's unresolved over there. So so there are some extra information from this bootstrap table. So this is kind of important, but most people also ignore that. And this is how to read it. So the bootstrapping is a pseudo resampling process. It's kind of a measure for repeatability and the accuracy of the data. And so it's, again, that's the robustness of the data measures for if there is any conflicting signal and so on. So, but also very important is the note here is that if the reconstruction method is wrong, then everything is wrong. So, for example, NJ neighbor joining or maximum parsimony, it has its weakness on reconstructing the trees. It has some bias, for example. And the bootstrap will not correct the inconsistency. So if the MP has some problem, I mean on making trees, then even though the bootstrap is very high, it doesn't necessarily mean that it's give you. I just don't want you to get a wrong idea about the support of the tree. Although it can be a very high support, but if it violates the assumption for neighbor joining, for example, then everything is wrong. So that's very important to keep in mind that although the higher the number only give you the idea about the internal support, not the true support in a sense. Okay, so it's the thing here, seeing the same thing. So here are just an example to tell you again about what is the differences between the accuracy and the precision. And the accuracy is a probability of obtaining a correct tree. So for example, it's like a shooting arrows. And if in the best case, everything is point to the same spot, and that's very accurate. But if you are always aiming nearby the center, then it still has a high accuracy in a sense. But sometimes the certain method can have a very high precision, but it does not necessarily mean that it's you are getting the right answer. So for example, you can, in this case, it has very high accuracy and precision. But in this case, the accuracy is actually not really good, but the precision is very good. So that means that the shooter is very good, and probably the gun is very good, or the bow is very good. So you always hit to the same spot, but it's actually off from the aim. So it will be the same for the phylogenetic tree in this case. So a very high bootstrap value was something like this one. It's 100% bootstrap value, but it's under the criteria of like neighbor joining or maximum parsimony. So only under those criteria you can give a very robust support, but it's not necessary to say this is the true tree. Okay, I think you can get this idea, the differences between these two. So just keep in mind on this part, on the bootstrap value. So there's a minor index you might sometimes encounter, and mostly actually for the morphological data. But actually, molecular data, you can also use this decay index. And the decay index is also called Bremer support because this was proposed by Alan Bremer, and was called by Bremer support by Michael Donoghue. And I think it's better to call the decay index anyway. So it's basically one index to calculate the differences if we want to break down a certain tree. I mean, what is the tree length for the shortest tree, and if we want to break down a branch and to support another relationship. So how many efforts you need to put on to break down those relationships. So it's also kind of a branch support to see how well your data is supporting a certain branch. So the idea is you can just get one of the most parsimony tree and try to get every tree has one step longer and generate a tree consensus. And if a particular branch is not supported, then the particular branch has a decay index 1. So just keep going on, just keep obtaining more and more until you resolve all the branch from the tree. So this is just a very quick example from here. This is a tree from the sequence of Arabidopsis and related taxa. And this is the single most parsimony tree, and with 110 steps. So you can collect those with 111 steps, and you got 3 trees. And this is the consensus, and you can just keep going on that. And these 3 trees, that's the consensus. So the branch to support a certain branch here, that has the decay index of 1, because with 1 step you can break down the tree. I mean, break down the branch. And you can keep doing that for this part, and you have some number. You can just worry about the number above the branch. So the higher the number on the branch, the decay index is, the more difficult to break down the relationship. So if the number is very low, that means that it's very easy to break down the relationship. So the sequence could be more closer to somewhere else. If the number is very high, it's always those two are grouping together. So this is also a very simple measure for the internal support for the branch. Okay. So this is the very basic tree evaluation process we got. And anyone got any questions so far?